start. I think the room is full. So thanks everyone to join our colloquium, also online. So it's a great pleasure to introduce our guest today, Professor Pietro Gambardella from ETH Zurich. I know the name should speak by itself, but it's also a great honor to introduce his history and CV. So he got his education in Italy, in Genova, in 1996, and then in 2000 he got a PhD at EPFL Lausanne. That was our common denominator, actually, where we ended up meeting at some point. And in 2002, he graduated and then continues his activity as a postdoc in Lausanne. And in 2003, he got two very remarkable prizes, the ABB Prize and the Priest Latzis Universitaire. These are two very well-known prizes in Switzerland. And then after that, he established his group in Barcelona. So he moved to Spain, and he became the head of the Atomic and Manipulation and Spectroscopy group. There, 1 year after he started the group, he got a ERC grant. So he got funding from the European Union, which is also a very prestigious award. And then in 2013, he wanted to move back to Switzerland, and he became a full professor at ETH Zurich, where he was also 2 years, for 2 years, head of the Department of Materials from 2021 and 2023. And 2 years ago, he also became fellow of the American Physical Society. So I summarized a bit all the prizes. The list is very long. I hope you can see the rest on the CV. But I don't want to take away more time from our speaker. So Pietro, the stage is yours. Let's welcome our speaker with a round of applause.
Thank you, Fabio, for the kind introduction, also for the invitation to give this colloquium. I'm very happy to be here in this place. It's an amazing place. So I've been here in 2017. There was no building, no STMs, of course, and I think this has come a very, very long way. It's a very impressive lab. So thank you for hosting me here, and also good afternoon to all of you. So the talk I would like to present today is a bit of an overview of phenomena that are generally concerned with spin-polarized electron transport and that go under the name of spin torques. And you certainly have heard a lot about this phenomena. However, generally, the terminology of spin torques is used in the context of spintronics. And it is described in a rather classical or semi-classical way, even though, of course, all the underlying phenomena are quantum in essence. But we also see these effects emerging prominently in quantum systems, meaning systems where the spin levels are quantized. And this also appears in STM, scanning tunneling microscopy experiment, very prominently. So before I start the talk, I'd like also to thank the really great contributions that my collaborators made over time. I'd like especially to highlight here in this context the work done by Stepan Kovaret, Richard Schlitz, Aishwarya Vishwakarma, Dominic Rucker, Tom Seifert, and Sebastian Stepanov, who has been leading all the STM studies done in Zurich that also I will present today. And then we have here other people that you see listed here contributed to some of the spintronics experiments that I will present today. So this is the outline. I will first give you a brief introduction on the concept of spin currents and charge spin conversion mechanism. Then discuss the phenomenology of spin torques in the spintronic field, also giving some practical examples taken from our own research of what you can actually do with spin torques, and then move on to discuss the effect of spin torques at the quantum level. And this is perhaps the area where you're more familiar with. And some of the experiments that we did also intersects with the ones you have done or are doing here. Okay. Good. So what spintronics is all about is connecting the electronic degrees of freedom, the charge degrees of freedom, with the local magnetization of a magnet. Okay. This typically occurs through the spin of the conduction electron themselves that couples to the local magnetic moments of a magnet. Right? And the idea is that you can either read out the magnetization by measuring conductance or resistance, and vice versa, influence the magnetization by applying the charge current. You certainly know about the classical spintronic effects, GMR, giant magnetic resistance, or tunneling magnetic resistance, whereby a initially unpolarized charge current passes through a first paramagnet, becomes spin polarized due to mainly to spin-independent conductivity as the electron scattering, and then passes through a non-magnetic spacer, a thin spacer, into a second ferromagnet. And this process can either have a low resistance for parallel magnetizations of the two magnets or anti-parallel. You get a high resistance, and this is used to read out the magnetization, specifically in sensing devices. And this type of sort of spintronic sensors are actually very big market today, not only as sensors to read information on magnetic hard drives, but also to measure position, speed in, for example, in cars or in industrial applications. So this is actually the biggest market for spintronic devices today. The reciprocal effect is that of writing a magnetic state using a spin current. Okay, here, I'm sorry, some of the fonts are probably not very well translated by this system, but the idea is that we send a charge current through such a typically magnetic tunnel junction or a spin valve. And again, the current is spin polarized by the first ferromagnet, and then transfers part of the spin polarization to a second ferromagnet, effectively torquing the magnetization and causing a rotation or a flip of this magnetic state. So here you see a resistance versus current curve, and you get switching in the two parallel or anti-parallel states. This is used in magnetic random access memory, but also relevant directions of research today essentially use these magnetic tunnel junctions or MTJs for neuromorphic type of computing applications and probabilistic computing. So the concept of a spin torque is actually quite old. It goes back to the 70s, similar to the tunneling magnetic resistance effect, where Luc Berger, who actually came from Lausanne as well, proposed that an electric current passing through a domain wall would have a spin polarization that is misaligned with respect to the spins in the domain wall, and therefore exert a torque on this spins. And this effect was also demonstrated in this early experiments, although it was not very widely recognized at the time. Okay. Then came other predictions. The most famous ones are actually listed here from Franceschi and Berger in '96, but there is a previous paper which is actually more relevant for tunneling experiments from Franceschi himself that discusses the spin polarized tunneling between two metallic electrodes separated by a tunnel barrier. And then here the sort of the modeling is a plane wave that is fully spin polarized on one side and tunnels to the other side. You have an exchange split band, and you have certain transmission and reflection coefficients. And we'll come back to this type of model later. Then soon after these predictions in the early 2000s came, or late 90s came the first experiments. And this go together with progress in nanofabrication and lithography, because in order to observe a spin torque on a macroscopic magnet, you need to sort of concentrate the current. You need actually to reduce the magnet to some mesoscopic or nanoscopic scale. So systems like point contacts, electrodeposited nanowires, and finally, nanopillars defined by E-beam lithography became popular, and these are actually where you see the clearest demonstration of magnetization reversal measured by the changing conductance as a function of current. So what is the concept of a torque? Let's discuss this very simply in terms of sort of first-year physics argument. Imagine you have a magnetization vector, and then you want to describe a torque acting on it. Very generally, you can decompose this torque into different components. Two are transverse to the magnetization. And these transverse component, if you define a, let's say, a spatial axis Z, then you can define it by these two cross products. This makes sure that you have two orthogonal components here, both orthogonal to M. And then you can also have a longitudinal torque, which is then parallel to M itself. Now, of course, these transverse components cause a rotation of the magnetization, whereas the longitudinal torque causes a shortening or elongation of M. And in spintronics is very often neglected because to first order, we think of the magnetization as a sort of a vector of fixed magnitude, which is not always the case. Okay. To complicate things a bit comes the terminology, which is not only sort of different, but also overlapping. So you get different effects called with the same name and vice versa. And so this these two different transverse components take the name of a field-like torque. This is perhaps the most appropriate one for a torque that is essentially has the same form as if you have a magnetic field along the z-axis. Right. This also takes this other name. In quantum electronics, this is called a spin torque, okay, which can be quite confusing. It's also called an exchange field, meaning the field that you put here, or a B1 field. Okay. Whereas the other torque here, this has a form of a dissipative torque, so it's called a damping-like torque, sometimes an anti-damping-like torque, sometimes a spin transfer torque, even though some people call also this a spin transfer torque. And in quantum electronics, it's often referred to as a spin accumulation, okay, which in spintronics is another thing. Okay, so it's a bit like, you know, calling things potatoes or potatoes as you like. So what is the actions of these two transverse torques? And that's also where the name comes from, right? So this first torque here, this transverse torque here, is equivalent to the torque given by a magnetic field pointing along the z-axis. The other torque is orthogonal to it. And this is essentially drives the magnetization towards the equilibrium position. So it's the damping term that eventually lets the magnetization go to equilibrium. Okay, so it's a necessary part. And in the classical Landau-Lifshitz-Gilbert equation, these two torques appear in this way, right? One causing precession, the other one damping. Now, if you apply a spin current, spin-polarized current, then you have, in principle, if you assume that M is a vector of constant magnitude, you have two possibilities for the torque that is due to injection of a conduction electron spins S here. These two can be described as a damping-like or a field-like term, and then they would have this form, right? So the field-like torque can be thought as a torque arising from the exchange interaction between the conduction electron spins and the local magnetization, hence this form here. And the damping-like torque is a dissipative torque that tends to align M and S together. Okay. And you can basically add them to the Landau-Lifshitz-Gilbert equation just by adding these two torques to this form. Okay. You can also express the torques as equivalent fields, right? So for the field-like torque, this is straightforward. For the damping-like torque, you get a field that is not really, it depends on the magnetization orientation, so it's better, is more correct to represent it as a torque. Okay. Good. So this is what happens when you inject such a spin-polarized current into a ferromagnet. You have these two types of torques. But this is not the only mechanism that can induce a torque. In fact, you have other types of spin currents. This is a spin current that flows together with a charge current, so it's a partially spin-polarized electric current. But you can also have processes where the direction of the charge current and the spin currents are decoupled, and you get a pure spin current made of an equal number of up spin-up electrons moving one way and spin-down electrons moving the opposite way. And this pure spin current can propagate orthogonally with respect to the direction of the primary current. Okay. So here you can decouple charge and spin. And most recently, people are also discussing the sort of equivalent effects for orbital magnetization, which is a very much debated concept nowadays. There are very interesting experiments and theoretical models that discuss this orbital currents and accumulation. So now I will give some examples of this transverse spin current, how they can be created, and what are their effects in terms of spin torques. Just to I should make clear that no matter the mechanism by which a spin current is created, the interaction with the local magnetization can be described always by the same type of physics. So one mechanism to create a transverse spin current is the spin Hall effect. The spin Hall effect works by applying an electric field to a conductor, which induces a primary charge current. And then inside the conductor itself, due to spin-orbit coupling, the trajectories of electrons which spin up or spin down are deviated, deflected in opposite ways. This can be either an intrinsic effect or an extrinsic effect due to spin-dependent scattering. And eventually this creates an accumulation of spins at the edges of a conductor, okay, with this symmetry that you see here. And these spins accumulate over a typical distance that is called the spin diffusion length, that for typical metal like platinum is the order of a few nanometers. And this parameter here is called the spin Hall angle. That's the ratio between the spin and the charge current, and it's typically 10% in a material like platinum. So this requires spin orbit coupling inside the material. Another effect that can create a transverse spin polarization is the Rush by Edelstein effect. This requires spin orbit coupling, but also inversion symmetry breaking in order to have essentially a potential gradient, an electric field at the interface of a material that then is relativistically seen by the electrons as a transverse, so-called Rush by magnetic fields that orients the spins of the conduction electrons. This has also been proved by a variety of surface science techniques, including ARPES and also STM. Okay, so then once you have this mechanism, either spin Hall effect or Rush by Edelsteins or similar effects, then generally you can think that you can accumulate spins with a well-defined polarization at the interface of a non-magnetic material. And then if you have a second magnetic layer deposited on top of it, these spins will diffuse. It will diffuse inside the ferromagnet. Then you have spin injection. And then we come to the torques, this interaction between S electrons and local electrons, localized electrons, that give rise to this damping-like and field-like spin torques, okay, which can also be seen as their respective effective fields. Okay. And so now these torques can essentially act on the magnetization, and we can measure the effects of these torques. We can measure it quite easily. Okay. One way is to consider what is the action of a torque on a magnetic domain wall. Right? So if you have a magnetic thin film, as schematized here, you typically have either Bloch walls with the spin in the wall itself pointing out of the plane of the magnetization, or a nail wall where the spin rotates in the plane of the magnetization. So you have either these two are the sort of most common type of walls in ultra-thin films. Now, if we consider spin injection from the bottom layer, these spins are diffusing upwards, right? What is the torque that is acting on these spins? Well, you have a field-like torque, but the important one here is the damping-like torque. The damping-like torque has the same direction as the injecting spins. This is a torque that tends to bring M and S together. Okay. Now, on a Bloch wall, this torque has no effect because essentially it is parallel to the wall magnetization itself. So the torque is effectively zero. on a nail wall, it has a maximum effects because the two spin orientations are orthogonal to each other. So this torque will act as an effective field that is oriented along the easy axis of the system. So this effective fields will effectively expand or contract the domains and move the domain walls. Now, this is an experiment to show this effect. It works with metallic systems, but here I choose to show it on a system where there is only a platinum non-magnetic layer where we produce this spin current using a spin Hall effect, for example. And then the magnetic layer is a thulium iron garnet, so it's an electrically insulating. There is no current flowing into this system. Okay, so here you see this is a MOG microscopy, a magneto-optical Kerr effect image of the system. Platinum is bright, the gray areas and everywhere underneath is thulium iron garnet. Okay, and we compare the field-induced nucleation. So we apply an out-of-plane field here, and here we pulse the current along this whole bar, right? And you can see that we see domain nucleation and expansion everywhere in this region here, depending on the field. Whereas when we look at the experiments where we pulse the current in the platinum current line, we have domain nucleation and expansion only in the region where underneath the platinum. Okay, so we can electrically torque and switch the magnetization in an insulating magnetic layer using this effect. And this is essentially induced by torques, spin flips at the interface between the metal and the insulating magnetic layer. Another effect, this is a similar system, so platinum thulium iron garnet here drawn on yttrium iron garnet is nucleating and moving skyrmions. So skyrmions are this sort of topological objects where the magnetization swirls around and has a core pointing out of plane, and then a sort of a nail type domain wall around it. Okay. And they cannot be produced by a continuous deformation of the magnetic texture of the lattice. So people speak of topological protection for this system. Okay. They can nonetheless be moved by this current-induced torques, as you see here, and that's again the action of the spin absorption by the domain walls surrounding these objects. We can go further and, for example, build magnetic circuits. These are so-called racetracks, where one can nucleate magnetic domains, propagate them by sending current through an underlying platinum layer, move the domain walls through regions that have ferromagnetic or antiferromagnetic coupling that we can fabricate, tuning the so-called Jagodzinski-Morier interaction and magnetic anisotropy. And then we can invert the direction of the magnetization in the domain walls and essentially produce so-called magnetic domain wall logic gates and perform logical operations. And this is all by currents. And this is the first effect that we noticed in our group is this current-induced magnetic switching, which also comes from domain wall nucleation and propagation. Here you have this platinum conductors where we send the current, and a small cobalt dot, which can have either up or down magnetization. This is a 500 nanometer dot. This is the platinum current line. We apply current pulses. This is the XMCD signal as a function of time in a pump probe experiment. So we send this current pulses multiple times, and we accumulate signal pixel by pixel in this experiment. And we see that during the current pulse, here is about 2 nanoseconds long, the magnetization inverts. Then we send a current pulse of opposite sign, the magnetization comes back. And we can also see how this occurs, right? You have nucleation of a domain wall, propagation of a domain wall, and then the opposite pulse comes, and this goes in reverse. And this process is determined by the essentially by the symmetry of the damping-like and field-like torques in the system. So we start from magnetization pointing up. We consider the fact that the magnetization at the edges of these dots is tilted, either inward or outward due to the Jawozinski-Mori interactions that favors non-collinear spin alignments. We then apply a magnetic field in plane that doesn't switch because it's a hard axis field, but it tilts more the spin on one side relative to the other side. And then we pulse the current, applying at the same time a damping-like and a field-like torque. And the action of these torques is such that they sort of counteract each other on the top side here, but help each other on the bottom side. And this is the nucleation point that we actually observe. So both torques are important to determine the nucleation point. And then the domain wall motion here is driven mostly by this damping-like torque. Now, this effect can be used in devices like magnetic tunnel junctions. And the nice thing is that now we can combine different sources of spin currents and therefore different flavors of spin torques. So we have this, spin torque from the spin Hall effect is called the spin orbit torque because the spin orbit coupling is very important. It's proportional to the current or voltage applied to the bottom electrode. But we can also apply a voltage to the top electrode and send the current through the stack of the MTJ, and this current will become spin polarized because of passing through the reference layer of the system and exert what is called the spin transfer torque because we transfer spin from one layer to another one. Okay. Plus, we have self-induced, so heating, Joule heating by the current, so self-heating. And we can also have an effect that is due to the fact that we apply a voltage to this top electrode that is effectively gating the free layer, changing a bit the electronic occupations of the states in the magnetic layer at the interface with the MgO barrier here, and that changes the magnetic anisotropy of these systems, something that you can also probe with STM cobalt atoms or iron atoms on Mg. It all comes from there. Okay, so these systems can actually be used in real devices. Here are devices made by IMEC in Leuven, where we have 3-terminal MTJs that are 80 nanometers in size, as you see here. And these are all developed on a CMOS compatible process. Okay. And we can use this system to probe the effects of the different torques. Here you have these are voltage switching traces as a function of time, single shot measurements for only spin transfer torque, for spin orbit torque with a little bit of spin transfer torque opposing the switching. Here, a little bit of spin transfer torque favoring the switching. And you see that this sort of, this sort of stochastic dynamics, long incubation times, variable reversal times, here becomes much more deterministic and sharp, right? And then we can play other tricks like applying an in-plane field also makes this distributions very sharp. And so in the end, we can squeeze the switching time distribution, incubation, and reversal to sub-nanosecond by combining these different effects. We can look at figures of merit, like critical voltages required to switch using these different flavors of spin torques, critical current, and then the product of the two times the pulse time is the critical energy. And we can see that by combining these different very short switching times and also gain in energy efficiency. Okay. And so one hopes that by combining these effects, we can extend the range of MTJ-based memories on non-volatile magnetic memories for random access type of RAM type of memories down to very very fast operation times, which would then be comparable to SRAMs with different scaling properties, cyclability, etc. Okay, so essentially at the spintronic level, right, with current-induced spin torques, you can do many things, several of which I have no time to discuss, but we can induce magnetization switching, domain wall, and skyrmion motions we've seen. We can also induce high-frequency oscillations and excite and detect spin waves. And because we do not need to pass a current through the magnetic materials, this works not only for metals, but also for magnetic insulators, 2D materials. It also works for antiferromagnets. So it's a very versatile effect. We can also detect the longitudinal spin torques, so absorption of spins that lead to a change of modulus of m, as opposed to the rotational spin torques. Right? This appears under processes that are essentially magnon creation or magnon annihilation by absorption of spins collinear with a local magnetization, and this appears, for example, in magnetoresistance measurement. Okay. Now, having said that, okay, we can sort of look a bit more in detail what is the nature of these torques, right? And so consider the two transverse components, the fill-like and the damping-like torque. And the fill-like torque, as I said, can be thought as originating from the exchange interaction between S conduction electrons and D local electrons in a typical paramagnet like iron or cobalt. And this torque is essentially a precessional torque. Okay. Whereas the damping-like torque, as we said, essentially induces a rotation of M towards S itself, and this is a dissipative torque. Okay. So how is the dissipative torque modeled in the spintronics community? This is a toy model. Of course, there are much more complex and better models than this. But essentially, you consider a system, this is the magnetic layer, with a classical magnetization and a spin split band structure. Okay. And then you have an incident current of spin polarized electrons. They have a certain orientation relative to the local magnetization. And this incident current, right, that you can describe like this in this basis, then can undergo spin-dependent reflection or transmission with different coefficients. Okay. And in doing so, these coefficients are different for spin up and spin down components of the incident electron. Okay. So now what happens is that as the spin current enters the ferromagnet, the states in which these electrons can live are at the Fermi level, because we inject, this is transport, we inject at the Fermi level. But then spin up and spin down components essentially belong to different bands, which means they have different wave vectors. So the spin of the injected electron precesses in space because K up and K down have different values. So you have a sort of precession in space as the spin travels inside the ferromagnet. Now you have many such electrons incident with different wave vectors, so from different parts of the Fermi surface, if you want. And their K wave vectors are different, and so their spatial precession has a different period, and that leads to dephasing of the spins of all electrons that are injected with respect to each other. Okay. And this dephasing essentially means that the transverse part of the injected spin, which is the one that exerts the rotational torque on M, is absorbed by the ferromagnet. And that is essentially because of conservation of angular momentum, it is acquired by the local magnetization. Okay. Now, this is a model that works up to a certain point, but it assumes that the magnetization is a classical vector, so entirely separable from S, that the magnitude of this vector is constant, there can be sudden spin flip reflections at the interface, and overall, it's a one electron single band model, which perhaps is not the most appropriate description for many such phenomena. Okay, so then can we gain some more insights into this process? Okay. And in particular, what happens at the quantum level when you consider the interaction between, let's say, a receiving spin and a traveling spin here in green, how should this quantum system be described? Right? You can think you have an entanglement of the states of the two spins, and then this entangled state has to evolve in the, for example, in the applied field or in the exchange field of the paramagnetic, right? And so can we probe some of these processes at the level of single or few spins? And of course, there are many theoretical models that have been developed over time, starting from the first one from Sanseski. Some earlier ones are developed in the context of quantum dots. Okay? And these are also some of those that we use later. And then there are also other models, some developed here as well, where one consider transports, again, at the quantum level in junctions with STM experimental setups in mind. And also this other models, these are full quantum mechanical models, but they do not consider, so there is no interband transition allowed or interorbital transition allowed in this system. Okay, so experimentally, which is then the part that's probably is most interesting to you, is how do we probe the effect of spin-polarized currents on quantum spins? And here comes spin-polarized STM. And here we know very well that we can use essentially the tunneling magnetoresistance between a magnetic tip and a magnetic atom to probe the orientation of the magnetic moment of the atom relative to the tip or vice versa. Okay, so there are many experiments started by the group of Wiesendanger this topic. Then, very interestingly, right, it was shown now 20 years ago that you can induce inelastic spin flip excitations by tunneling onto single or even coupled magnetic atoms. You can measure the energies of the spin flip excitations. And also that you can induce a change of population by essentially injecting spin-polarized electrons from a tip that can be either, they can have a magnetic moment that is either parallel or anti-parallel to that of a local spin. Okay. And this essentially means inducing transition from, say, the ground state to excited levels, which can also have a reverse magnetic moment. Okay, so in the language of spintronics, this effect would be called the longitudinal spin torque, right? Whereas in STM it's called spin pumping, and spin pumping in spintronics is a different effect. So it's another example of confusing terminology. Okay, and then comes the EPR STM here. I showed this in case you don't know, right? But of course, this is a very nice method to probe single spins and coupled spins in surfaces. Good. So this is how we do EPR STM in Zurich. So we start from a commercial STM system, and we added RF cabling in a coaxial wire that then terminates with this exposed section parallel to the tip. This works as an antenna that is capacitively coupled to the STM tip and effectively allows us to produce a rather strong RF bias in the junction. And this you also know very well. I only present this in case there's somebody following by chance from other fields. That is that the detection mechanism of EPR, this sort of the standard one, is based on the homodyne signal between the applied RF voltage and the fact that as a spin precesses around the field axis, the conductance, or if you want, the TMR, gives you a frequency component at the same frequency as that of the RF voltage, and then the two produce a DC current that can be measured by a locking technique. Okay. And so the idea is that if the RF bias also induces an oscillation of the atom in the inhomogeneous field of the tip, you can have a time-dependent magnetic fields that excites EPR. But we know now that this mechanism is actually not the main one for sure taking place. Okay. So these are some of our early experiments on iron and titanium atoms. Essentially, we were trying to reproduce the results obtained in Almaden and here by the group of Andreas. And we also then did some analysis, multiplet analysis of the iron excitations, and came up with this sort of model where we have to consider longitudinal EPR, not only EPR not only transverse EPR to drive resonances in this. But more interesting to us came this system here, and this is a system where we use pentacene molecules as organic radicals. So they're supposed to have spin 1/2. This is what we prove. And they are also absorbed on MgO as the decoupling layer from the silver substrate. So we have two monolayer MgO, and then we deposit pentacene. You can see it here together with iron atoms that we use to then pick up and make a spin-polarized tip. Okay. Now, the nice thing about pentacene is that it has very well-defined molecular orbitals, and in particular, the LUMO orbitals upon absorption on MgO, they split, and you get a singly occupied molecular orbital because of charge transfer from the substrate, and then a singly unoccupied molecular orbitals that remains empty. And this we can probe by simply varying the bias of the STM tip, right, and probe the occupied and unoccupied states, and we see in this very well-defined orbital shapes as expected for a spin 1/2. Then we can excite EPR STM. This turns out to be, so we can essentially map the current and the EPR signal, and we see an EPR signal that is fully delocalized over the structure of the molecule. This confirms that this is indeed an organic radical and that we're probing a delocalized spin density. And then the signal varies because essentially the influence of the Doppler field is different from the tip, is different on different sides of the molecules. So that gives this sort of resonance slices that change depending on the tip position. Now, when we measure EPR, right, these are the full spectra that we measured, starting from zero field at different frequencies, right? And you will recognize the dispersing features here. This is the expected EPR behavior, plus a zero field feature that when we first saw it, we were sort of puzzled by it, but in the end, we now know this has to be there, and it's in fact a very significant part of the measurements. Okay. By plotting this dispersion here, we can also derive the magnetic moment of the molecule, which corresponds exactly to spin 1/2. Now, if we look at when we have this system here, right, the interesting thing is that we have this well-defined molecular orbital resonances. And so we can measure EPR, say, in the gap, right? And these are the spectra that we measure as a function of applied field at different frequencies. And we see that the signal scales such that it increases with field, and that is expected because essentially this is a paramagnetic molecule that we are polarizing more and more with the applied field. We're also measuring at 4.5 Kelvin, so we need field to overcome thermal redistributions. So this is expected from standard population arguments of the spin doublet. If we measure near the orbit, the molecular orbital resonances, however, we find an intense signal that where the intensity doesn't depend on applied field. That's already an indication that something else is going on here. And also, if we analyze the line shape of the signal, this is in gap, this is in correspondence of one of the molecular orbitals, you'll see that's quite different. Okay, these are the intensity scalings. Again, one is frequency or field independent, the other one is strongly dependent. And we can analyze this line shape and extract a symmetric component, which is dominant here, and an antisymmetric component, which is more dominant in the in-gap state. So how do we explain these different features and this bias dependence? So the most convenient model is actually a quantum dot model, where we have only two allowed electronic levels, a singly occupied orbital and a doubly occupied orbitals with charging energy, so Coulomb energy U. Okay, that is coupled with different coupling terms to the tip, which is magnetic, and a non-magnetic electron. And one coupling with the substrate is actually stronger than the other tip. So then we have to consider different regimes of tunneling. For example, if these molecular levels are not aligned with the Fermi level of the two electrodes, then we're in the co-tunneling regimes, and when we are aligned, we'll be in the sequential tunneling regime. So what happens when we have transport through this well-defined electronic levels? Okay. Well, suppose that the electronic level is singly occupied and has a spin up, and suppose that the tip is also spin polarized up, right? This means that tunneling is not permitted in this situation because this doubly occupied level here can only accept a spin down level. So this is effectively a regime of spin blockade. On the other hand, we can have an open transport channel if the spin on the molecule is opposite to that of the tip. So in this case, you can charge the molecule, right? So you can charge it, which effectively means that you have just a doubly occupied energy level up here, okay? And then this state will then relax, so discharge, but it discharge to the substrate where there is no spin selection. So you have 50-50 probability of discharging spin up or spin down, okay? And that means that you can only feel spin up, but you can empty both spin up and spin down. So the system effectively remains polarized into the state, the polarization state of the tip. So we have a strong initialization of the spin on the molecule. And once that initialization has occurred, the system is spin blocked. So now what happens in this case? Okay, you have polarized the local spin in blue parallel to the tip polarization, okay, which effectively means going from this state on the Bloch sphere to this state, assuming the tip is polarized along this line. Okay, then, sorry, this is a, then we apply a magnetic field, okay, and the pentacene spin here starts to precess in the applied field, okay. It precesses, and this precession essentially lifts the spin blockade, and so we can have now tunneling, and this part of the slide. Okay, so we go from a spin blockaded state to a non-spin blockaded state in an applied field. Okay, and in this case, we open the transport channel. So here the conductance is larger than here. Okay, the sign of peak, or so the sign of this curve, this depends on the sign of the PMR, but essentially here, the high field, we have higher conductance. Here we have a lower conductance. Okay, and this is the charge dynamics as a function of time for the spin blockaded part. This is initialization, and this is the sort of the lifting of the spin blockade by the applied field. This effect has also a name. It's called a Hanle precession, which gives essentially a Hanle magnetoresistance. Okay, so and it doesn't require any RF. It just requires initialization by a spin-polarized current and then precession of the spin in a magnetic field. So it's called also DC Hanle effect. Okay. Similar effects are observed also in spintronic devices. Now, what about the RF part, so the AC part? Okay. Now, if we tune the bias to this molecular orbital resonances, this means we can actually tunnel in and out of these orbitals. Okay. So we initialize the spins, but then what happens when we have an applied field is that the spin will precess at the Larmor frequency, right? And at the same time, we are modulating with the RF bias the tunneling probability. Okay. And so if we match the RF frequency to the Larmor frequency, we're essentially, we can match the tunneling probability with the precession, and we can realize a state where we have a maximum probability of injecting electron when the spin is essentially always blockading the transport. Okay. So we initialize the molecular orbital, and then this spin starts to precess. And at the same time, when we want to re-inject again an electron, because we have a higher RF bias, the system cannot, so the conductance is low because we have a spin blockade. It's a dynamic spin blockade. And so this means that the spin on the molecule can stay longer in the coherent precessing state. Okay. And that's why we have we observe an EPR effect in this case. So it's essentially an AC version of a DC Hanle effect. And that's what gives this EPR peaks. So we can model this, all of these effects together, and here you see the evolution as a function of sort of frequency and fields, and this corresponds nicely to what we measure. Okay, so summarizing, we have two different regimes for this, for exciting EPR. We have a regime where we do not tunnel directly into the molecular orbitals where the spin is, okay? And so this is a regime where the dynamics is mostly corresponding to an oscillating magnetic field, B1. That's the field-like torque, okay? And this oscillating magnetic field is essentially the exchange field between tip and molecule. But then when we can actually have transport, so real transport between tip and molecular orbitals, then we enter into a dissipative regime of sequential tunneling, so electrons can really tunnel in and out of the state, and that is giving a dissipative component and incoherent dynamics. We can model also the line shapes that are expected for the field-like torque driving and the damping-like torque driving, and the two together. We can compare these with the behavior of the asymmetric and symmetric components in the line shape as a function of RF bias. And we see that indeed, as upon increasing the bias, we see that one component tends to saturate, whereas another one changes from a sort of field-dominated to a transport-dominated effect here that scales quadratically with the applied voltage, and that is what we expect for this damping-like torque mechanism because of it depends on the current as well as on the TMR. Now, interestingly, if you measure the tunneling magnetic resistance of a magnetic tunnel junction, so like a big object, some 100 nanometers in diameter, and you inject, so you apply an RF bias, you'll see similar effects. You'll see, you can excite also here a paramagnetic resonance in this case, with a line shape that is a sum of symmetric and antisymmetric contributions corresponding to damping-like and field-like torques. So there is really a parallel between these dynamics that we see. We can describe this type of dynamics by including a field-like driving term here in the Rabi rate, in a dissipative term in this sort of modified Bloch equations type. So we expect also that the field-like torque induces coherent dynamics and the damping-like torque induces instead incoherent dynamics. We can prove that by pulsed experiments. We see that we have well-defined Rabi oscillations when the bias is tuned in the gap between SOMO and SUMO. And these oscillations attenuate when we move towards the molecular orbital resonances, right? So we go from a more coherent to a more incoherent regime. Okay. And we can eventually fully model these processes by a reduced density matrix approach. This is the work of Dominic Ruckert, also including a dissipation term in a sort of modified Lindblad form. And what we see is the following. So I'll sketch here, I'll show you what happens for the DC field-like torque. So this is the torque that originates just from exchange, magnetic field exchange between tip and molecule. It's essentially due to virtual electron tunneling. There is no real transport involved. So you'll see that the current, this is the tunneling current, stays 0, okay? And while the spin precesses in the magnetic field of the tip, this is the tip polarization, and the blue is the trajectory of the spin. The effect of the damping-like torque component instead is that of initializing the spin of the molecule along the direction of the tip polarization, and that once that occurs, then the current goes to 0 because the system is spin blockade. That's showing again, sorry. Okay, now we see the AC driving. Okay, so AC driving, now we have this oscillating exchange field, the B1 effect. And then again, in this model, we have no actual transport, but we have this coherent dynamics of the field-driven spin. Okay. Whereas the damping-like component works in this way. So here you see now we have an oscillating AC current, okay, and that is due to the fact that we have over time, when averaging over many events, we have electrons that can tunnel in and out of the molecule. So every time an electron goes out, right, then the current can go up because we can refill the molecular state. Precession starts again, and this process repeats itself, right? And this means we have then this type of precessional dynamics in this case. Okay, do I still have 5 minutes? Okay, maybe you want to stop a couple of minutes. Okay, sorry for being long. Okay, so then this is a part that comes as more recent experiments, also that we analyzed with the help of Chris Bolt, Jose Reina, and Nicolas Lorente, and is trying to understand nonlinearities in the transport. And the nonlinearities are evident also if we extend our measurements to detect higher harmonics. And in fact, by exciting, for example, pentacene at 9 gigahertz, you observe not only the main peak, the first harmonic, but also a peak at twice the expected field. And this also scales, as you see here, So we have these processes that eventually tell us that indeed we are exciting a signal at 2 omega. Okay. And that is interesting for several reasons. One is practical, so we can extend the EPR signal beyond the actual bandwidth of your cables, your RF electronics. And the other is investigating and understanding what causes this nonlinear dynamics. And in fact, we can also measure third harmonic if we extend part of this measure. Okay. So, and this higher harmonic signals is quite high, right? So 20% of first harmonic is I think a large signal. It scales in a nonlinear way with applied RF voltage. And so clearly this means we have some nonlinear driving in the system. Okay. And here comes the model developed by Jose and Chris, which is based on the Anderson impurity model and then the coupling of the impurity to magnetic electrons by hopping. And the key idea here is that the RF voltage bias modulation induces time-dependent hopping proportional to the applied RF, but the tunnel current goes as the square of the hopping term. And so even though you apply a linear RF voltage, you can have a quadratic response in coupling. Okay. And the model reproduces the observed second harmonic frequencies and also for a certain range of parameters, also the relative intensity is quite well. So is the higher harmonic signal due to feel-like or damping-like torques? It actually appears in both transport regimes, so both at low bias in the gap or near the molecular orbital resonances. And this is because the tunnel coupling enters in all transport regimes, and that means that it is a feature that comes naturally from considering time-dependent transport when you apply a time-dependent bias. Okay. So it's not due to vibrations or field rectifications or stray fields, as we also supposed earlier on a few years ago. So these are the conclusions for the EPR STM part, right? We can detect EPR in a molecule with a distributed charge density. We identify field-like and damping-like spin torque contributions to EPR and also associate them to DC and AC Hanley type of effects. We can model this behavior by including a two-level quantum dot systems exchange coupled to a magnetic electrode. We should consider both the population and coherences in all of these processes. And we can detect second harmonic phenomena that are related to transport. Okay. Some final considerations. How do we connect back with the idea of spin transfer torques in spintronic systems, right? Remember, I told you that most of models consider classical magnetization, consider a single band with an exchange splitting. But in reality, right, we know that much of the basis of spintronics is due to the fact that we can consider S conduction electrons as separate from D local electrons. And this is also what explains the decrease of the resistivity in the typical ferromagnetic metals below Tc. Right? This happens because above Tc, you have large probability of SD electron scattering independent of spins for the two spin channels. Right? But below Tc, one scattering channel closes. And so then this gives a reduction of resistivity, and it's the basis for the so-called two-channel model, so where you can separate the dynamics in the transport of spin-up and spin-down electrons in metals. Okay. This also shows that what is important is to consider the interaction between two types of orbitals, S and D. And so based on the results I presented before from pentacene, we can associate the spin torques in a sort of microscopic spintronic system, the field-like torque due to virtual SD exchange processes, and the damping-like torque due to real SD interband transitions, meaning you really transfer electrons from one state in one band to another state into another band. And this is a dissipative process. So that offers a view to interpret at the quantum level many of the phenomena that are observed in spintronics. And with that, I thank you for your attention and your patience.
Thank you very much, Pietro, for the very comprehensive talk.
Long
and
topic.
then there's room for questions. Stefan already lining up. Thank you for the talk. I was wondering, so in the model, especially for the coherent part of the Hanle model, there is no requirement for selection rules, right? At least not for like conservation of angular momentum. Do I understand correct? Or?
I mean, you do have conservation of angular momentum, right? In a way, you cannot explain, it cannot escape the system, right?
But so I would say that in principle, you could drive also spins that are not, like not simply one half. Is it correct?
Yes.
Okay. So do you think this could explain the driving on iron? That was the first atom that was driven. And related question, do you think this driving then can be extended to single molecule magnets or like, say, spins that are not simply, let's say, spin one half model?
I mean, for example, the models that were made for explaining the iron APR also based on the so-called piezoelectric coupling mechanism, right? These are, you can also think of this model as just take the fact that you have an oscillating magnetic field in the junction, and that will give you the EPR. And so as long as you have that, and for iron, you would have to have also a field gradient that gives you longitudinal EPR, but it's still field driven, so you can still associate it with a field-like torque, if you want, right? And I think the difference between the piezoelectric coupling model is that really you don't need the atom to oscillate physically in the junction, right? You can just think of this as being due to the modulation of the bias, right? This is also what Chris and Nicolas Laurent proposed. So that would work, and I think the damping-like mechanism can always be active as well. But of course, if you transfer one electron at a time, then there is only certain fraction of angular momentum that you can change in the system.
So it's more related on how much angular momentum you can pump into the system, more than like a real selection rule.
I would say the two are related, but yeah.
Yes, but you don't have to involve, let's say, a coupling between the electric field or the electromagnetic field and your atom.
I mean, what do you mean by the coupling of the electromagnetic field and the atom? So
because maybe, okay, I still have to digest well the model, but it seems that the driving is just given by a pre-precession or a Larmor precession, and then a modulation on your spin pumping.
So the dissipative mechanism, so the damping-like spin torque EPR, is indeed you initialize the spin, the spin evolves in the magnetic field, so it precesses, and then you have this dynamic spin blockade that essentially lets the spin precess while you're trying to tunnel, but it doesn't allow the tunneling. So in fact, the resonance that we observe in the dissipative damping-like torque is a resonance that corresponds to a decrease of the conductivity. It's always in the same direction as the DC Hanle effect. So the sign here, whether these are up or down peaks, depends on the TMR sign, but essentially these resonances always means low conductance, high conductance, low conductance, high conductance.
Okay. Yeah, thank you.
Hi, thank you for the nice talk. Can you maybe tell me this spin transfer torque mechanism for EPR? Is there any dependence on the T1 time or the charge or the lifetime of the quantum dot or the charge state of the quantum dot?
Well, the charge state has to be essentially it's always almost nearly 1, right? So it's only because the coupling with the substrate is very strong. So one of the two couplings this coupling here is very strong. That means that as soon as you doubly charge this dot, an electron can escape, right? And so you can only charge the dot when you're out of the spin blockade regime for a very short time. So the average charge state is mostly 1, I would say. This is also what you see here. Yeah.
There is no dependence on T1.
Well, I mean, we always have the same molecule on the same substrate, so yeah, we don't have a proper statistics of that. I would say, I mean, of course, if your T1 is short, then you also influence T2, and then all the effects decrease, all the resonance effects decrease in that sense, for sure.
Thanks.
Hello.
Hi.
My question is about this torque-driven mechanism. Is it local effect? So it's possible to drive the spin only in the presence of the tunneling current. And we have this example of 3-atom structure from QNS there. We can drive and remote qubit without tunneling current. So does this model can be extended to this example? And my second question is about the molecule. So you mentioned that the molecule is a radical, so it contains an unpaired electron. What about the localization of this electron and how this can, I don't know, change some properties that you work on the molecule with the localized electron instead of measuring this in the single atom?
So to the first question, right, whether all this mechanism, essentially the spin torque dynamics, can also then be transferred in some way to a sort of a spectator atom or to other spin systems that are coupled to the first one. That is possible, and we are also doing experiments on this type of systems. And there is also a theory by Michael Flaté at Iowa State that considers similar processes. So this is certainly a very interesting point, and I think it will give results in the future. Future for us means 2 or 3 years publication time, when we're good. The second question, as far as we can say, right, the spin density is sort of uniformly distributed and really follows the molecular orbital distribution. Okay, so spin follows charge. What is important to observe, the type of dynamics that we observe is really more the localization in energy. So the fact that you can really define a regime where you tunnel not in this spin containing molecular orbital or directly into these orbitals. And then you can clearly distinguish what is this sort of co-tunneling field-like dynamics from the sequential tunneling dissipative dynamics. So this to have well-defined molecular orbital resonances is very important.
Last question.
Thanks. Thanks, very nice. I actually have a question to the first part. Because I see there is a lot of connection from the, we would say like large devices to the single atoms and molecules. Is there also an operating regime or some way to use the former devices but clearly see the quantum behavior? So if you go to very low currents with this, I forgot the name of the company, these RAMs, for example, or something like this.
Mm-hmm.
Can you see a connection between these two size regimes?
Well, it would be very nice, right? If we could do quantum operations with mesoscopic spintronic devices, it would be fantastic. I think you know, from the level of qubit operations, that's not possible, right? You have too much decoherence. But there are certainly, you know, as you see, many effects have a very nice correspondence to each other. And then, you know, even at the level of microscopic magnetic systems, in the end, the magnetization is a quantum object, right? You have quantum excitations that are magnons. So you do have quantum phenomena to consider also in the larger system, right? The point is that you cannot treat this with a sort of two-level system, and then yeah. But yeah, that is a very interesting. I think there is probably more work to do in this area.
Okay, I think he has to catch up catch a flight later, so please let our speaker leave. So thanks again, Pietro, for the
Thank you very much.
and thanks everybody for joining the show.